Assalamu alaikum. It's our eighth lecture of Principal Methods and Applications of Nuclear Tracks. And in this lecture, we will start with carbon dating and then we're supposed to solve some problems. Okay, so let's start. As you know that as we did in lecture number 7, that we started carbon dating, and you know that carbon 14 is basically the most radioactive. Okay, because carbon 14 isotope is radioactive, that's why we can say that it's basically unstable. And the half life of carbon 14 is 5370 years. Okay, and whenever your carbon 14 decays, it's supposed to decay into carbon 12. So the practical example is whenever body dies, either it's human body or animal body, so carbon 14 decays into the carbon 12. Okay, so basically carbon dating is basically the ratio. Okay, decrease in ratio carbon 14 divided by carbon 12, and the minimum range for this, which is denoted by r naught, and that is equals to 1.3 multiplies by 10 raised to minus 12. This is basically the minimum range. Okay, for the case of carbon dating concern. Okay, and we supposed to fetch information means we can fetch information, we can get off information. Okay, nearly thousands and up to 25,000 years ago. Okay, so we can find the age of any specimen if that specimen is either 1000 or less than 25,000 years ago. So this concept carbon dating is very crucial to find, okay, the age of some specimen nearly thousands up to 25,000 years ago. Okay, so for that our practical example is basically the age of Iceman. So this is basically a concept that age of Iceman, and it's basically the age is calculated as its age is 5,300 years. Okay, so we have a problem here for the case of carbon dating. So the problem is a piece of charcoal contains 25 grams of carbon. Okay, so you have a piece of charcoal. Okay, you know what is charcoal? Basically, look, and it contains 25 grams of carbon. Okay, so it has 25 gram of carbon, means mass is given of carbon, and that is 25 grams. Is found in some ruins of ancient city. Okay, the sample shows carbon 14 activity and its range is given, which is 25 decay per minute. Okay, and how long has the tree from which the charcoal came being dead? Okay, so you have to find the time. Okay, how long has the tree from which the charcoal came being death? Okay, so how you can solve this problem? To solve this problem, first of all, you know to how you can find, okay, basically the time period of this. So to find the time period, there is a relation, and the relation is, let me write here. Okay, your solution of for this problem is basically, first of all, you know about the formula for the case of okay, time period. T basically equals to minus 1 by our lambda. Okay, ln r divided by r naught. Okay, and this is basically r at time t. Okay, and this is at time 0, and this lambda is basically the decay constant. Okay, and this time is basically the time period. If you want, this is how you can find the time period of any body. Okay, in this case you have to find. So let's find. So for that, to find this, we need this ratio r by r naught. So first of all, we have to find this ratio, which is r divided by r naught. So how you can find the ratio r divided by r naught? So you can find there is a relation of r divided by r naught, and that is equals to basically r, and r naught converts into lambda n naught. Okay, and this is for the case of carbon 14. Let me show here carbon 14. Okay, now this changes into how you can again convert this r divided by r naught again can be converted into r divided by lambda and naught. The new thing which should be added here is basically r naught, which is the, you can see here, which is the minimum radius. So radian must be included in this scenario. Okay, so that's all. Now again there is another conversion here, and this r divided by r naught again can be converted into r divided by, and this r naught, this lambda, this r naught. Okay, and this n naught is converted into small n and na, which is the Avogadro's number. Now the final conversion for the ratio of r divided by r naught is again r divided by, now what should we have to do here? We have to put the value of n, you know, that is the number of moles. So the number of moles is equals to mass in gram divided by molar mass. So you have to write here, and you have to put the value of lambda. Okay, you have to put the value of lambda, and you know the value of lambda is basically, you know that the value of basically lambda is ln of 2. Okay, ln of 2 divided by t 1 by 2, where lambda is the decay constant. As you can see here, I also wrote the formula. This is basically the formula list. Okay, so you can see this formula I already showed in 12th number. K equals to ln of 2 t divided by t 1 by 2. Okay, so this here I consider k as my decay constant. It's your choice, you can take any decay constant. Okay, like lambda, k, or any n. Okay, anything. So you know that the decay constant is equals to this. Now you have to put the value of decay constant. So other things as it is, r naught as it is, r naught. Okay, r naught, and then put the value of lambda, which is decay constant, which is ln of 2 divided by t power 1 by 2. Up goes upside, so it becomes t 1 by 2. Okay, and this n, small n, is the number of moles. It's convert into mass in gram, means small m divided by capital M, means molar mass. Okay, and this Avogadro's number as it is. Okay, now this capital M goes upside. Now your final relation of r divided by r naught becomes equals to capital M r t 1 by 2, means half life, r naught, which is the minimum radius. Okay, and ln of 2 small m and na, which is the Avogadro's number. Now you just have to put the values. Now capital M, what is the value of capital M? You know that it's given, like you know that the mass of carbon, because in our this scenario carbon is concerned, and you know that the mass of carbon is 12. So capital M should be 12. Okay, so 12 multiplies by r, the r value is given, which is 250. Okay, 250, and the value of half-life of this, you know that the half-life of carbon 14 is basically this, as I mentioned here, 5370 years. So you have to put here 5370 years divided by, put the value of r naught, you know that 1.1 what is the value of r naught? You know that 1.3 into 10 raised to power minus 12, and the value of ln of 2 multiplies by ln of 2 multiplies by okay, this is the molar mass value is 12 of carbon, and this is the mass in grams. Small m is basically the mass in grams, and the mass in gram is given this small m, which is 25. So here 25, and the Avogadro's value, you know that 6.02 multiplies by 10 raised to power 23. Okay, so let first conserve unit. The unit of this 12, because this is capital M, so it is basically uh, gram per mole, and the unit of this is basically per minute. Okay, means minute minus 1. We just have to checking the units. Okay, either units are good or not. And this is a year, because this is a half-life, so it's uh, basically it's year divided by these units. There is no unit of this, and ln of 2 is also constant, and the mass in gram unit is grams, so grams have to be multiplied by and the Avogadro's number has a unit of mole minus 1. Mole minus 1. So this mole goes upside and this mole goes downside, so this cancels with this mole, and this grams cancels with this gram. This is per minute and this is year, so this is per minute, so move this to downside. Now there is a unit of year per minute. Okay, but we have to reduce this unit. So to reduce this unit, what we have to do, have to convert in seconds, and we know that in 1 year basically there is how many seconds? 3.15 into 10 raised to power 7 seconds, and in 1 minute is basically 60 seconds. How you can calculate this? You have just calculated by this 3 6, because 1 year has 365 days, multiply by, okay, multiplies by here 24. Okay, means 24 hours, multiply by 60 minutes into 60 seconds. After calculating this, you will get this seconds, 3.15 into 10 raised to power 7 seconds, okay, in 1 year. So what you have to do to concise your units, you have to multiply this also. So you have to multiply here. Okay, 3 multiply 10 raised to power 7 here, means 3.15 here, divided by 60, 60 here in denominator. So after calculating, you will get your answer, and your answer of that ratio r divided by r naught is basically equals to 0.667. So there is no unit of this ratio, because when this r naught goes here, basically r and r naught units are same, so there is no any unit of this ratio, because we have to find the, okay, time period of it to decays. So we know that this is the formula. Now you have to put the ratio here. Now t becomes equals to minus 1 divided by lambda, but you know the value of lambda is this, ln of 2 t power 1 by 2, so it becomes ln of 2, and denominator t power 1 by 2 comes outside, so it becomes in numerator t power 1 by 2 here. Okay, after putting the value of lambda here. Okay, and ln of r divided by r naught, and you already find it this, so you have to put 0.667 here. Now what you have to do, putting the values, T minus, and half-life, you know that basically equals to this. For the case of carbon 14, 5370, 5370 divided by ln of 2, and ln of 0.667, and your final answer for the half-life, sorry, for the time being uh, being dead for this charcoal is basically 3.4 multiplied by 10 raised to power 3 years. Okay, so this is how you can find, okay, any time period for the any specimen came being dead. Okay, how long your specimen being dead. Okay, this is how you can find. So that's all for this problem. There is another problem. Okay, so we have to solve that problem also in this lecture. So let's start another problem of carbon dating. Again, you can see this is our second problem, and our second problem is basically consider an ancient mummy having mass of 125 grams. So an ancient mummy found in Egypt, and the mass of is basically 125 grams. Okay, show a sample show a carbon 14 activity of 350 decay per minute. Okay, so the activity is given, means R value is given, which is 350 decay per minute. Okay, what you have to find, you have to find the age of that mummy. So you know that how you can find any age of any sample, any specimen, if you know their mass and their activity rate. Okay, so to find is again the same scenario. You have to start, first of all write the value of given, and this is your solution for this problem. And here the mass in grams is given, means small m is given, which is 125 grams, whereas your activity is given for the case of carbon 14, and that is basically equals to 350 decay per minute. Okay, decay per minute. So what you have to do, you have to find the age of that mummy, means you have to find the time, how long it goes for that mummy. So you know that our final relation, first of all you have to find t, and you know that t basically equals to minus 1 our lambda ln of r divided by r naught. Okay, whereas to find first of all this ratio, how you can find, we know that r our r naught, the final relation of r our r naught is basically, you know, that is equals to capital R m, okay, t 1 by 2, which is the half-life, again divided by r naught multiplies by ln of 2, and multiplies by small m multiplies by na, which is the Avogadro's number. Just putting the values we will get r. We know that r is basically the value is given, which is 350 here. So 3 again 350 here multiplies by mass, and the mass of the molar mass of the carbon is again 12. Okay, multiply by half-life of this carbon, you know that basically 5730 divided by r naught, you know that 1.3 into 10 raised to power minus 12 multiplies by ln of 2 multiplies by mass in grams, and mass in grams is given, which is 125 multiplies by Avogadro number, you know that 6.02 into 10 raised to power 23. And you know that as we did in previous numerical, to conserve, to same the units, we have to multiply it by year by minute, and you know that 1 year has 1.3 sorry 3.15. Okay, up in numerator multiply by 3.15 into 10 raised power 7, and in denominator multiplies by 60 seconds. So seconds cancels with seconds, and the ratio of this has no unit. Okay, because both are same variables, ratio has no unit. Okay, so after calculating this, we get our ratio of r by r naught, and that is equals to 0.1866. So this is the ratio. Now what you have to do is just put in this value of t is equals to minus 1 by lambda, and you know that lambda is basically equals to ln of 2 divided by t 1 by 2. Okay, so this ln of 2 here in divided by l t power 1 by 2 comes in denominator becomes t 1 by 2 here. Okay, again ln of r by r naught, and the answer is this, so it is become 0.1866. Putting the value here, so t becomes equals to half-life value. You know that for the case of carbon 14, half-life is this 5370 divided here ln of 2, ln of 2, again ln of 0.1866. So after calculating, you will get your final answer, and your final answer is 1.3 into 10 raised to power 4 years. Okay, so this is how you can find the age of any sample. Okay, the age of any material specimen. In this problem concerned, we are going to find the age of that mummy, and the age of that mummy is 1.3 into 10 raised to power 4 years. So this is how you can find the old age by carbon dating. So that's all for today's lecture number 8 of our implications, methods, and working of nuclear tracks. So thanks for watching. Stay tuned with us. We will upload more interesting lectures for this course. Allah Hafiz.